Okay, so remember from the last set of notes we talked about how the usual maximum likelihood estimator tends to bias or systematically underestimate the variance. That would be a problem, right? Because then we would be um, underestimating our residual variance and our other variances associated with our variance components, and that will bias our results also for our fixed effect inferences. So we don't want that. So a solution that was devised many, over 20 years ago was residual maximum likelihood method. It is basically a modification where we use the residuals of the fixed effects model, estimate our variances using maximum likelihood based methods on those residuals, and then using those variance estimates as the correct solution, we get our best estimators back for the fix. So kind of plugging them back in to that solution and then obtaining those fixed effects. Notice that the fixed effects originally estimated in step 1 could differ from those estimated in step 3. So, this I would normally, when I've taught statistical computing in the past, we would go through all the details of this. We're really just going to use this in this course. We can use maximum likelihood estimators in this course to compare our nested models that differ with respect to their fixed or random terms, but we can only use those Rimmel estimates to compare nested models that differ in their random terms. Remember, the first thing that Rimmel does is get rid of the fixed components in the model. So it would not be useful as a comparison model if we're trying to also refine our fixed terms in the model. So to compare models using a likelihood approach, we would, number 1, take negative 2 times the difference of the log likelihoods of our two nested models. Treat that, of course, becomes a chi-square distribution, as we've all learned in our statistical inference classes, and then we reject when that p-value gets small enough. Okay, so we'll practice this in class. This is a standard model comparison scenario that you've seen in categorical data, as well as the theory behind it in your probably Stat 5381 is where that would get taught. That negative 2 times the log likelihood is called that deviance, and we have a maximum likelihood deviance as well as a Rimmel deviance. You can't directly compare those. Those are two different things. Okay, we can compare models also using our information criterion, the AIC or the BIC, and that just applies a penalty to that deviance function, the negative 2 times the log likelihood. K, of course, is your number of parameters, so these 2 versus log of n are the two deviances applied, not deviances, penalties applied. The chi-square approximation doesn't always work all that great. The asymptotics don't always kick in, so to say. So to get better p-values, we can simulate that distribution of the chi-square test. R will do that for us. We'll take a look at the CAVS example in R in class so that we can see how that can get done. I skipped over that CAVS example and the Bayesian statistics in brief for the online notes because I wanted to handle that in class instead. But I do want to talk about crossed versus nested models. All of our factorial models that we looked at in the past chapters, the ones that included more than one factor, multi-factor models, were crossed. And we know that they're crossed. We didn't call them crossed at the time, but they were crossed because each level of each factor appeared with each level of the other factor. So that's a fully carried out factorial design when we look at every single A, B combination and make sure it's included as a level in the experiment. And we've seen many cases of that. That is what we are used to at this point. Let's compare and contrast that to what if we have a factor B that nests within factor A? Then each level of A has a completely different set of B factors or levels. So this might be a case where maybe factor A is a factor that uh, contains some sort of structure and determines what kinds of level B can be observed. Okay, we're going to see cases starting now where this nesting is more appropriate than crossing. You may be wondering, why haven't we talked about nested factors yet? It hasn't been a really important thing to bring up until now because the nested factor like B here, which nests in factor A, B is almost always random most times. I think I would need to think. I can't think off the top of my head and come up with something right now, but I think B could be fixed. But most of the time, B is going to be random. Think of this as like I again, I go back to my Cal College University days where everything I learned about these linear models and experimental design, I learned in the context of with a bunch of animal science and agricultural science people around me. So imagine you're breeding cows or bulls and cows, and you have, say, male bulls that are typically mated with many, many females, especially when you get a good bull with good DNA, let's just say. And so you would have females nested within males because certain females are only mated with certain males. And so I could see that in some cases as being fixed. Okay, so think about it that way. Animal studies nesting comes up all the time. And so this is my context that I will go to automatically in my brain. I know that may be more or less relevant for you, but we'll try to think of other ways to think about nesting studies. For notation, the effect B nested in A, we'd write as B within A. So notice the parentheses that are used here. And when we talk about the effect within our linear model, we don't just call it BJ, even though in a typical crossed experiment, this would just be beta J, but we have beta J nested within I, just to remind us that those levels of B depend on what level of A that we are in, or may be affected by the level of A that we're in. Again, here, think about mating cows with bulls. If an I is a particular bull, then there's a different set of cows that are mated with that bull. Okay? If B nests in A, then A and B cannot interact. That doesn't make sense here. Okay? You can also have C nested in B and nested in A. Again, I can't think of anything not having to do with breeding animals here. So imagine you look at the offspring from the cows that are mated with bulls, and then you could have an effect for their offspring if you measure something having to do with their offspring. Again, genetics experiment. In my classes, a lot of the animal science students were doing all kinds of genetics experiments to get these bulls that were going to be good for mating. And I could see a C nested in B, nested in A for one of those experiments. Okay, so it could be different though once you involve a C factor. We could have C nested within AB combinations. So AB is a crossed combination in the traditional sense that we've always seen up until now, and then C is nested in there. So again, AB could be like, I don't know, imagine A is a bull still, and it's crossed with some other factor having to do with the, I don't know, the method of fertilization or something. Then C could be nested in there where C is still the cow. Almost anything's possible, just I'm sure researchers come up with all kinds of crazy ways to nest and cross and so forth. Like I mentioned on the previous slide, nested factors are almost always random, but okay, so good. Gary agrees with me. There are examples where they could be fixed. I still have a hard time thinking about that. Here's some, you can tell Gary's also from a Cal College like me, where we have a lot of animal studies. So suppose we have 6 randomly chosen male rats. Each male rat is bred to 5 different female rats, assumed from a random selection of all female rats. Then we measure the 4 week growth of each pup resulting from that mating. In this case, just like the cow and bull study, females nested in male. We have a different set of females for each male. We're not going to mate females with one male, then go mate them with another, because then it's unclear. The heritage is unclear there. Okay, so pups are nested within each female. Is pup an effect or is it an error? Don't call pups an error. That's just mean. Perhaps it could be either. I'm not sure. I agree with Gary. Does it really matter? I'm not sure. What if we have 2 measurements for each pup? Then would that be the error? I would think so. It just depends on how you're doing it. A pup could be error, and I think that would be okay in a lot of cases. Even in our most basic fixed model like this thing, we could have written errors nested within treatment. So that would be the pup nested within the I and the J, the male and female here. That's a weirdness. That should be a J, not an N. Because errors are nested, we just don't have to point it out until we've nested other things, okay? But if you think about those errors are always nested. Just pointing it out here. Now here's another one that's not about breeding animals, thank God. So we're interested in the effects of apple variety and treatment on growing. We have 3 varieties of apples. From each variety, we choose 6 apples at random. Each apple is then cut into 4 slices, and the 4 slices from the apple are then randomly assigned to 4 treatments: a control, orange juice, lemon juice, and salt water. So this is to keep them from oxidizing, presumably. In this design, apples are nested in variety, right? Because you can't have an apple slice from 2 different varieties. You can't cross that. But both variety and individual apple cross within treatment. Right. I had to think about that. So each treatment appears with each variety and each apple. But there are different apples for each variety. That makes sense. Okay. That is a nested design by necessity, right? By physical necessity. All right, so make sure you understand that. There's a little bit more discussion about this in the book, but we will also talk about this a lot in class. The nuance, making sure we've got all these kind of nuanced ideas here. Just as a recap, why do we use nesting? Well, we have subsample treatments. It's often constrained by, like in the apple example, we just have to do it that way by necessity. It's constrained by logistics. Okay, you do things differently at different sites, or you got apples from certain varieties. There's all kinds of reasons. It's by necessity or logistics, I would say. And the correlation structure among the units can actually be directly modeled when you nest things, so that has a nice application. We'll be doing lots of examples to make sure we understand this.